Hello all. Today we will be discussing the solutions for assignment 11. Firstly, we will just go over the terminologies for the flip-flop and the latch. For the flip-flop, you have TCCQ, which is your contamination delay, which is nothing but the minimum delay of the flop, which is this. You have TPCQ, which is the propagation delay, which is the highest delay from the clock to the HQ. Then you have your setup time, which is the time before which the data must be ready, and you have the hold time, the time in for which the data must be stable after the clock arises, right? Similarly, now we look at the terminologies for a latch-based system. You have first TCCQ, a contamination. You have a contamination delay, TCCQ, which is again this similar definition, which is a minimum delay. Again, you have TPCQ. Then you have something called as TCDQ, because here in the latch, the D element can change because it is transparent throughout the entire region. You have new terminal, so two more new terms, which is TCDQ and TPDQ, just as the names suggest. They have the contamination from D to Q and propagation from D to Q. Again, you have setup time, you know uh, from the sampling edge, not from this edge, from the sampling edge, which is this. And you have your hold time from the sampling edge again. If you have a positive latch, the sampling edge is the falling edge, right? So now that we've refreshed our terminologies, we will go into the questions. Uh, Assignment 11, question 1. Is the following figure a positive edge triggered flip flop? So it is a positive edge triggered flip flop. Why? Because the first one is a negative latch. If you see here, the latch is controlled by clock bar on the N and clock on the P, right? And clock here and clock bar. So this is a positive latch and this is a negative latch. Therefore, you have your you this the first latch is uh, is transparent at this edge. The second latch is transparent at this at this edge, right? But the first latch is opaque. you know Latch number, the element 1 is opaque here. It is, sorry, once again, if you look at it, if you look at the clock signals, right, when the clock is 1, the second latch is transparent. When the clock is 0, L2 is transparent, L1 is opaque. Now L2 is opaque, L1 is transparent. So only this common area exists, which is the positive. Therefore it's a positive edge triggered flip-flop. If one removes sequential element 2 from figure 1, the remaining circuit will be a negative latch, because you remove the positive latch, you remain with a negative latch. Right? Questions numbers 3 to 4. Which of the following data will reach QM? So, uh, in you assume the figure 1, the circuit of figure 1, since it is a positive edge triggered uh, flip-flop, D1 will reach, because here is the positive edge. So I'll just mark the positive edges here. Whatever, whichever signal is ready before the positive edge, those signals will reach QM, right? So D1, D3, D4 all are ready, but D2 occurs after the positive edge, and it also changes before this next edge comes. Therefore, D2 will not be ready. Similarly, for whatever passes through this will pass till the end, right? D2 is not ready. Assuming that the transistors have terminal currents as per the unified current model, the circuit of figure 1 may stop working for a clock frequency less than Fmin. So if you assume that transistors have terminal currents as per the unified current model, if you go back and look at the unified current model, you do not have any, you do not have any leakage terminologies. That is, when VGS is less than VTH, it's absolutely zero current. Therefore, in such a case, you will have, you can operate at any Fmin. at any frequency, right? Those don't have an F-min. But when there is a subthreshold leakage, you cannot operate in any clock frequency. You need to operate at greater than a certain frequency. Otherwise, this particular node over here, right, it will leak and discharge. And let's say one was there, it will leak through this transistors, this path, and it may become zero over time. So if it is very, very slow, let's say 1 hertz, it would leak all the way and it would have become zero before the next edge comes, right? Therefore, in an ideal case, when there is subthreshold leakage, you cannot operate that at any frequency. Question 7. In the circuit of figure 1, with input T, internal node QM and Q, noise in the input can disturb the internal state when clock equal to 1. So when clock is a particular value, 1 or a 0, it cannot disturb. Only when only when at the positive edge, right? Only when at why? Because when it is 1, if there is a noise, it does not pass through all the way till Q, right? Because as you know, from this, what we've written, L2 is transparent when, let's say there's a noise here, but L2 is transparent, which is this is transparent, whereas this is opaque. So, when the clock is 1, whatever happens at T, the latch L1 is opaque. So none of that can even pass through and even reach QM. You leave Q. It cannot even reach QM. Therefore, the answer to this question is false. Moving on, look at, you can observe question, this figure for question 8 to 10, right? So what is the type of sequential element shown in figure 3? So it says it's a negative latch. Why is it a negative latch? What qualifies it as a negative latch? When clock is equal to 0, whatever data is there, it can pass through like this. It features this node. Since it and it can pass through this inverter and can finally reach out to Q. So therefore, whenever it is 0, any change in D will directly appear at Q. Therefore, it's a negative latch. What is TDQ of the sequential element shown in figure 3? So it is TG1 plus I1 plus I3. What is TDQ? Which is this delay plus I1 plus I3. You just need to traverse the paths through which, it goes, and 7 nanoseconds is the value. What is the T setup of the sequential element shown in figure 3? Again, TG1 plus I1 plus I2. What is the T setup, right? So what is the time required for you to be stable? If so, any time, so you start over here, you go to I1, and you should not only go and complete I3, this should also have affected I2, and the data should remain. That is the aim of T setup. Let's say if you've only waited till the data changes at 7 nanoseconds before the clock uh, falls. So since in this case it is a negative latch, right? So uh, let in a negative latch, if you draw the clock, this this is your sampling edge. So let's say it waits only till 7 nanoseconds. Then over here, let's say the D has changed and D has remained only for 7 nanoseconds. Then what will happen? The D will have enough time to reach Q. But as soon as the clock hits, the old value of Q will be restored due to I2 on I1, and the Q's value will change back. Therefore, you need to wait all the way till the loop stabilizes. Therefore, this TG1 plus uh, TI1 plus TI2. Once the loop stabilizes, TI3 is just an additional amount of delay it takes to reflect. Therefore, the answer here over here is 8 nanoseconds, which is this. Driver strength is not an issue. So here in this case we're using break the feedback design, right? So what do you mean by breaking the feedback? When this transistor, when clock equal to 0, there is a particular path that is broken. It is not trying to overpower. If you were to take the example of overpowering feedback, let's say uh, that there was this kind of a setup, right? And this TG has to now overpower and pass the value over here. Whereas over here, it has broken the feedback of, it has deactivated this loop, and you can finally write back till I1, and I2 will settle after the value, is after the clock and clock bar are, uh, lifted. In a sense, 0 becomes 1 and 1 becomes 0 over here, then this loop gets stabilized, right? What is T clock to Q? TG1 plus I1 plus I3. This is exactly what we saw over in the beginning also. What takes the total time it takes for it to appear on Q. Okay. What is the hold time of this particular configuration? In this configuration, you do not need to hold for any time because it is a latch-based system. As soon as the data is as soon as the data is sampled over there, you can immediately change it at the input. At least here, you can change at the input, and that does not have a path to propagate at all, as it is cut off immediately, right? So as soon as the clock changes, the TG does not even uh, as soon as the clock becomes 1, let's say you change the data to from 1 to 0, nothing happens because the clock and clock bar instantaneously change, and they do not even let the value of D to propagate inside. So therefore there's no hold time issue over here. uh, Question 14. The circuit shown in figure 4 is a positive edge triggered flip-flop. Why? Because you have you know a clock connected here, uh, clock clock bar, clock bar, right? So basically, if you look at this, this is a negative latch, and this is a positive uh, latch, right? So you have a flip-flop which arises due to this negative and followed by positive latches configuration, right? There's a positive edge triggered flip-flop. So one removes sequential element 1 from the circuit. So if you remove sequential element 1, this is a positive latch. So positive latch remains. What is the setup of the sequencing element shown in figure 4? So the sequencing element shown in figure 4, setup time is what is being asked. Setup time is, the total time TG1 plus it's given as TG1 plus T I1 plus I2. I1. So basically, the setup time is the total time required for you to pass through TG1, I1, and I2. Why? Because if you do not wait for so much time, if the data is not ready for so much time before, and let's say immediately changes, then by the time the clock comes and samples it and stores, the recombination will not happen. Basically, this TG2 will not have the value, so that this element will store the value, right? So therefore, the value is TG1 plus I1 plus I2. What is the T clock to Q of the sequencing element shown in figure 4? TG3 plus, it says TG3 plus I3. So T clock to Q is as soon as you give clock, what is the clock to Q? TG3 plus I3. I is where you have your output being flowed, right? So as soon as you switch, let's say the clock changes from uh, 0 to 1 over here, what is the delay for the Q to appear? It is this delay, right? So uh, just from here to here is the delay. Yes, so that is 16 nanoseconds. So yes, If you have any more questions, please let me know in the comment section. Thank you.